Imagine standing on a rugged, fog-drenched mountainside, blindfolded. Your only goal is to make it to the valley floor. In machine learning, this mountain represents the error or loss of a neural network. Altitude is how wrong the AI is. You could try jumping in random directions, hoping to eventually land lower down. But when a modern AI has millions of parameters, that is the equivalent of trying to find the valley by randomly teleporting across thousands of dimensions. You will never stumble into the right answer by chance. This 3D topographical grid represents the terrain. To navigate it, the network uses a mathematical compass called the gradient. By nudging a single parameter, the network measures exactly how the slope changes beneath its feet, calculating an arrow that points up the steepest nearby incline. By simply flipping the sign of that gradient vector, the network determines the exact direction of steepest descent. It takes a step down, recalculates the slope, and repeats. This blind, localized process of feeling out the terrain one step at a time is the mechanical engine driving all modern artificial intelligence. This basic algorithmic loop is called vanilla gradient descent. The network evaluates the slope, multiplies it by a fixed step size, known as the learning rate, updates its internal weights, and takes a step. This perfect, smooth 3D bowl illustrates a convex problem. Because there is only one unambiguous bottom, taking evenly spaced, direct steps will always lead you exactly to the center. But notice the fuel required to make this work. To measure that perfectly accurate slope, the network has to process the entire training dataset for every single step it takes. When you are training on millions of images, holding all that data in memory just to take one step is computationally impossible. The mathematically pure path is simply too heavy to walk. To bypass this data bottleneck, the industry uses stochastic mini-batch gradient descent. Instead of evaluating the whole dataset, it estimates the slope using a tiny, random handful of data. Look at these two lines descending the slope. The smooth path is full batch. The jagged line is mini batch. It frequently steps wrong, but evaluating small batches so quickly lets it easily overtake the perfect line, reaching the bottom in a fraction of the time. Perfectly accurate calculations are the enemy of machine learning. Embracing noise and approximation makes training massive neural networks feasible. This diagram illustrates a ravine, curving steeply in one direction but flat in another. Standard descent bounces uselessly across the walls. To fix this, researchers borrowed momentum. Accumulating past gradients makes the algorithm act like a heavy ball, dampening violent side-to-side oscillations. Different terrain requires different approaches. Deep learning pioneers built highly specialized algorithms to automatically adapt step sizes. One of the most famous, RMS-prop, was actually introduced by Geoffrey Hinton during an online Coursera lecture. Adaptive optimizers, like Adam, work by monitoring the landscape. They perform small, cautious updates on steep, frequently occurring features, like walking on ice, and make large, confident updates on rare, flat features. Training a neural network today relies on simulating physical forces. You are using inertia, gravity, and friction to force math into its lowest energy state. A deep neural network's loss landscape is not a simple, smooth bowl. It is a chaotic terrain littered with topological traps. Notice how these points behave on this bumpy profile. A step size that is too small freezes the network, taking microscopic steps on a tiny hill. A step size too large launches the algorithm completely off the graph. Now take this 3D saddle point. It curves up in one dimension and down in another. In the flat center, the slope is 0, and a vanilla algorithm permanently halts. This is where the erratic noise of mini-batch descent becomes an asset. Random sampling makes the point jitter, knocking it off the knife edge so it continues descending. Without the inherent chaos of random data sampling, deep learning would be paralyzed, caught on the flat plateaus and stationary points that litter high-dimensional space. There is a strict limitation to gradient descent. It only sees the ground immediately beneath it. It can never see the whole mountain, which means it finds a local minimum, but not necessarily the absolute global minimum. The final resulting performance of the AI is dictated by where you drop it on the mountain, the random initial weights, and the sequence of noisy steps it takes on the way down. A moment of wonder. The chaotic path eventually settles into a dark, fog-shrouded valley, completely unaware of its broader surroundings. Because this walk is blind and localized, the final model is just one of many possible configurations. We can verify that the version we found works, but we have no way to prove it is the most effective one possible.